Well, good morning, everybody. We have an exciting video today for you. Um, I'm just thrilled that we finally got this prepared and ready to go. We're going to talk about gravity versus density, and we're going to show absolutely that, that things don't fall because of density. And of course, we can't forget our joke of the week. Why did the chicken cross the road? Why did the chicken cross the road? So here is my experiment. Uh, Over to the left here, you can see uh, uh, the scientific method, so we can be sure we're following the correct steps. Um, First of all, there are many flat earth videos that make claims that gravity does not exist, that there's no force holding things down, and that density is what makes things fall. We hear all these cries, and I know you've seen videos. Why does a helium balloon rise? Or how can a force be strong enough to hold down billions of gallons of seawater and yet be weak enough to allow a butterfly to fly? You've seen the videos, and I'm sure you've seen the debunks. So we're not going to talk about that in this video, but I think you'll see some answers if your mind is open to the truth. So the first step, our scientific question that we've come up with is, can we determine whether or not density can produce the effects that scientists attribute to gravity? Uh, can we drop objects of differing volume, mass, and density from different heights to see whether they drop at the same time or not? Here's my background research. Um, Again, uh, we hear in flat Earth videos all the time that scientists don't know what gravity is, uh, and there have been all these disputes back and forth, back and forth. Uh, but we know what the effects of gravity are. We may not know what gravity is or where it comes from, but we do know what its effects are. Both Newton and Einstein had ideas of gravity. Um, Sometimes we hear that Einstein replaced Newton, and so Newtonian gravity is no longer uh, evident. Newton Newtonian gravity is from a classical point of view, and Einstein from his general relativity. Einstein did not invalidate or replace Newton. Now let me repeat that. Einstein did not invalidate or replace Newton. Newtonian gravity is merely relativity with set conditions. So, or Einsteinian gravity covers different solution or different conditions, uh, and it does work for the same conditions as Newtonian gravity, but Newtonian gravity still works, and it's much easier to use in everyday uh, use. And you can look that up. I have a link here you can look. Um, Currently, very advanced theoretical physicists. So currently, due to time and space studies, and this has been a big thing in the news lately, time and space, and efforts to reconcile the four fundamental forces. There are four fundamental forces: strong nuclear force, weak nuclear force, electromagnetism, and gravity. And there is a far-reaching the theory of everything, and you may have to look that up if you've never heard of that. But I can guarantee you that none of those things prohibit the fact that the effects of gravity are evident, quantifiable, and measurable. Okay, so the next thing, my hypothesis is the following. So I have a null and an alternate hypothesis. The null hypothesis, density causes objects to fall and to be held to the earth. We're going to call this one the status quo. The alternate hypothesis, density does not cause objects to fall and be held to the earth. This is the challenger. Let me explain that the null hypothesis and the alternate have to be mutually exclusive, and they have to include everything. So you can't make up hypotheses unless they fit those criteria. Here are the variables that I used, and I defined them to be letters so that I could use them in equations. You can see what those are. Some of the definitions that we use: density is equal to mass over volume. Note that mass is a property of matter. It has to do with how much matter you have. Volume, same thing. It has to do with how much matter you have. So density is mass over volume. Relative density, we hear all the time now, the latest flat earth term. Relative density is density divided by the density of water. And this is the same as specific gravity. Specific weight is weight divided by volume, and specific volume is 1 over the density. Note, I put at the bottom here, note that increasing the amount of a substance, whether it's weight or volume, if you increase the amount of a substance, it does not increase the density, only the volume and the mass. So keep that in mind. Here is the data I used to set up my experiment. This may be a little long, but I hope you can understand. The first thing I did, I got me some balls, tennis ball, which I had to look up the statistics on that. The tennis ball weighs 0.125 pounds. I bought an exercise ball, which was defined to be 6 pounds. And then my son had this spherical rock he's very proud of, and he wanted to use that. So I weighed that and it's 9 pounds roughly. So then I converted those numbers to mass. And if you look down here at the bottom below the table, I used two equations to convert to mass. You have to first convert pounds to newtons. Newtons is the SI version, and then you convert newtons into kilograms. So there I have the mass. The tennis ball, of course, is very small. The exercise ball, much bigger, and the spherical rock is pretty much double the exercise ball in mass. The density then, you remember the density was mass over volume. So density for the tennis ball was 0.36. For the exercise ball, 1.44. And for the rock was 2.77. And then I had some calculations where I got the volume. So what I did is I measured the circumference around the middle in inches, and then divided by 2 pi, and I got the radius. So the radius in inches, there it is, 1.32, 3.02, and 2.86 inches. Converted that to centimeters, and there are the 3 centimeter values. And then once you have the radius, you can calculate volume. Volume is 4/3 pi r cubed. And so the tennis ball was 157.5 centimeters cubed. The exercise ball was 1890 centimeters cubed, and the spherical rock was 1606 centimeters cubed. The ambient information, the temperature was 86 degrees Fahrenheit, 30 degrees Celsius. The humidity was 0. It's very dry here, and so there was no humidity that day. So I actually did 3 drops, and we got 4 videos out of that. So the first 2 drops I dropped off of my garage roof, 12 feet 4 inches, which I measured with a measuring tape, 3.76 meters. The third one I dropped off of the second story, 27 feet 4 inches, which was 7.11 meters. So there's the first part of my setup data, and here is my first drop. Let's see if I can get this to play. There we go. You can see we have the 3 balls. We tried doing it by hand.
Yes, I can.
Okay. 1, 2,
Which didn't
3.
work real well. But you see they drop pretty much at the same time. And hit the ground at the same time. Okay, here is one in slow motion. Oops, is this the,
I'll say 1, 2, 3, and then 3 drop.
I think
Okay?
this is the same one.
Yes, I can.
Okay. 1, 2, 3.
Maybe that, yeah, let's see if I can. This one is the one in slow motion. And you can see I got a little tray to try to drop them better at the same time. And still, the tennis ball was real hard to drop at the same time as the other two. So you can see how they drop here. Again, this was slow motion, so it took us a while to get everything. Oh, guess I didn't start the video, huh? Excuse me for that.
Make sure they're
It's the
evenly
first
spaced.
time I've done video. So here we go, slow motion. That large fellow there to the right, that's my youngest son, 6'5". Here we go. So again, you can see they kind of fell at the same time. The exercise ball got all squashed when it hit the ground.
Ready?
Here's my, I did the second drop over again using the tray. You can see there, they all fell at the same time. Here is the one from the second story.
Okay,
Go.
1, 2, 3, go.
You can see we had a lot of trouble getting that tennis ball to drop at the same time, to start at the same time as the other two. So those were my tests, my analysis of those videos. The videos themselves were the collection of the data and part of the analysis. And although the three balls did not start exactly together, they stayed in the pattern that they started all the way to the ground. This was the same pattern for the lower height and the upper height. And the visible acceleration was the same for each of the three. It's more evident in the slow motion video if you look there, if you watch that one again. So the interpretation for me is that I had some error because of the way I dropped the balls. It was very hard for me to figure out how to get them to drop at the same time. But even with those errors, you can see they pretty clearly hit the ground at the same time. You can see that three balls had very different densities. Again, I included the data down here. You can see that the three balls had different densities, weights, and volumes. You need to recall that the air density is 0.001. So I don't see how that small a number can cause the balls to fall together. It's obvious that this could not be density, and that no matter what the density, size, or the weights, or the volume, the balls fall together. So I'm going to have to reject my null hypothesis and accept the alternative, which is that density does not cause objects to fall and be held to the earth. This experiment you're already watching is published on YouTube. And yes, we're going to do a retest. I asked Anti-Flatter to help me do a retest. Before you watch his video, note that he is in Australia, which is the opposite side of the world from me, so very clearly different ambient information. He's using different setup data. He's not using balls. So now let's welcome your friend and mine, Anti-Flatter. Give him a round of applause.
Kia ora everybody, I am Anti-Flatter, and thank you David for allowing me on your show today. Now today I have a demonstration which will help us understand whether it is just density and buoyancy or whether there is a force, let's call it gravity, that is affecting all objects universally. How we've done this is we have two bottles. One of them is filled with a small amount of liquid, the other with a large amount of liquid. Both these bottles will be of the same shape, so hopefully that will take air resistance out of the equation. We're then simply going to line the bottles up and drop them. If the bottles full at the exact same rate, then it can be assumed that there is a universal force pulling these objects down towards the center of mass, being the Earth. If the objects fall at a different rate, then we can confirm that it is in fact the density of the objects which are creating the difference. So, let's head outside and let's test this, shall we?
Here's his drop.
Well, there you have it. The two objects fell at the exact same rate. But, just to make sure that we're not being biased, let's start flipping these bottles around. Let's have the bottle cap of the lighter object at the bottom. Same result. How about we flip it again and let's have the bottle cap of the heavier object facing the ground. And same again. Well, it appears both these objects, one heavy and one light, are falling at the exact same rate. Exactly what is predicted by the current theory of gravity. David, again, thank you so much for having me on. Back to you.
That was his video. I'm hoping that the sound came out. So my conclusions after all this, it's clear to see that both experiments, my original and Anti-Flatter's retest, offer the same exact results, proving that density or relative density cannot reproduce our results. There's one and only one possible result, and Anti-Flatter said it best. It absolutely has to be gravity without question. So let me ask any flat earther watching this video, repeat the experiment and prove to me that it cannot be gravity if you can. My last comment, go over to Andy Flatter's channel and give him a subscribe. I'll include a link in the description. Now you've all been waiting for the joke of the week. Do you know why the chicken crossed the road? So why did the chicken cross the road? We have two possibilities. Einstein would say the chicken didn't cross the road. The road passed beneath the chicken. Newton, classic explanation. Chickens at rest tend to stay at rest. Chickens in motion tend to cross roads. Hope you enjoyed this experiment, and we'll see you again next week.